All right. Welcome back to week 6, which is actually taking place in week 7. Um, we will continue on with now damped. Oops, let's go back up here. Damped. Oops, that's back one. No. This is going great. Damped forced vibrations. We haven't shown the figure that we're basing this thing on. So we have a spring with a K here, but we also have a damper, C, and we have a mass. Now what's also changed is we've applied some type of force that changes. I guess we've been using P, so it'll P, and it has a magnitude, and it has some cyclic component to it, so it's going back and forth and back and forth and back and forth. And if we did our differential, the FBD and the IBD, we end up with this form for this simple process. And our goal here is to solve solve this equation. Now, this is a similar one that we could use in case, instead of having a force down here, we had, and I'll draw it slightly over here. If we instead we had some type of base right here, and a spring, and a damper, sorry, both on here on the mass, and we shook this thing up and down a del. All right, so that del 0 would be the magnitude of how much we shook it, right? So we would have two separate situations that equate in many ways to the same thing. All right, so here is what we have to do for this is to solve x. We need the complementary part, and we need the particular part, because this is a non-homogeneous differential equation because it doesn't equal 0 over there to the side. And so since the particular part is our main concern, we will write out, and in this case, we did a phase. We included a phase in there for a pretty good reason. It helps us to cancel things out. So it's like a little trick that somehow we magically had to know ahead of time. So we'll say, since the particular part is our main concern, we'll call that X part. And we're going to say that it has, I'm looking over this right here. I don't know why I have O's everywhere. I've placed O's everywhere. I'm going to put this O into here and just be cool with it. So we have a sine of omega ft, and then we placed a phase. That phase is going to help us get rid of some additional aspects of this. Well, like I mentioned, this is sort of a trick in the background, and I have to pause for a minute. So we take the particular part, the derivative, and we end up getting xo times omega f times the cosine of omega ft plus this arbitrary phase angle that we haven't used yet for anything. I'm still looking at this arbitrary angle. I think it might have to be a negative one. Anyway, let's just keep going with this. X double dot particular solution thing. We're going to have a negative xo omega f squared times sine omega ft. And now I'm starting to question whether that phase angle needs to be a positive or negative phase angle. All right, so we substitute this back in, and there's a lot of stuff that has to come back into this equation. So let's start way over on the left. And negative m omega f squared xo sine of omega ft. I'm keeping with my positive phase, but I'm not quite certain of it. Now I'm going to have to put in the next one, and that's going to be c times xo omega f cosine omega f plus phase angle, and then next is going to be plus k xo times the sine omega f t plus phase angle. That f doesn't look like it's a subscript anymore, does it? Make it look like a subscript. Okay, a little bit better. And then lastly, equal to PO times the sine of omega ft. Now, through this, you might have noticed there's something different than we did for the undamped portion. We can't just cancel out sines and cosines. What we can do is come up with a little trick, a little scheme. These always bothered me, but we're just doing it because our motivation is to get rid of some stuff and to simplify some things. So maybe if you just hit the accept button, that we have to do something to get rid of some things. So when you say that omega, so when omega ft plus phase angle equals 0, right? So when that happens, you would find that c omega f times x0 is equal to p0 sine of phi. Oh, that's why we did it. I see. Okay. So I knew there was something going on here with a little bit of a trick, right? You see all those. We're just gonna just for our own sake to simplify life. We decided that this would make a lot more sense. Okay, so bear with me here. Let me fix all of these things. Let's take them in red, right? So let's make them all minuses. It didn't really matter. This was an arbitrary thing. So we'll say that right there. All right. So what we could say now is we substitute when this happens. That means now this guy, it becomes phi, right? Because before he was this, right? But now he is the phase angle, right? So continuing on. So that's the explanation for that. And then also we could say when omega f t minus phi is equal to pi over 2, right there. Now the rest of the thing, okay, so up above, when it was 0, everything went away except for the damping one and this guy who turned into the phase angle. We can say that the bottom one, what we end up with is k minus m omega f squared times xo equals PO times the cosine of phase angle. All right. So we did that to try to simplify this. This guy over here, he was too difficult to get. So we said, okay, in these two scenarios, because it was cycling between 0 and pi over 2, and pi, and then 3 pi over 2, and so forth and so on, right, as it's going through in time. So it's going back and forth between 0 and 90 degrees, basically. So here's these two extremes. So if that's true, what we could do to equate what the behavior is of these two things that are true, they're just not necessarily true at the same time. Sometimes this is true. Let me see. Let me go to another. Sometimes this is true, and sometimes this is true. Right? They're not always true at the same time. But if we wanted to get the magnitude of them, what we could do is square both of them and add them together. That is a very common engineering trick, right? So if we square both of them and add them together, we end up with, let's see if I can find this right here. We'll go k minus m omega f squared, square that, plus c omega f squared times xo squared, right? Because we squared both of that and we squared that. And then equals And now we're going to take, I don't want to write it out, but I guess I can go ahead and do it. We can go PO squared times, I guess I'll do it in the other order. Sine squared phi plus cosine squared phi, and well, I guess I used parentheses, not brackets. We recognize that that's equal to 1. This thing up here was a strategy gimmick to try to get rid of that portion. But now we have this relationship, and we could write it out. We take the square root of both things and say XO is going to be PO divided by the square root of K minus M omega F squared, whole thing squared, plus C omega F squared. Right, and if we wanted to know the phase of this, we should also, because this is a relationship. Remember what we did with the undamped version. We took a box. Something's happening inside this box, and we have an in, and we have an out. And our goal is to find what the relationship is of the out to the in is. This is the out, and that's the in. We can also, because sometimes the phase information is important to us, we could find the phase by taking the inverse tangent, if we want, of C omega F over K minus M omega F squared. And notably, if we want to, and we will in a second, we can manipulate these equations by dividing through by K and also collecting some things and writing them out in different ways. So we want to compare this, by the way. So let me get rid of my phase because I don't necessarily need that all the time. But let me compare this, what we just wrote right here, to the undamped version of it. So where we get an undamped version of it is going to be XO, and I didn't mean to make them big X's, so that doesn't really matter, is PO over square root of K minus M omega F squared. Now, I know we wrote it in a different way, but along the way, this is one of the forms that we had. So we could compare those two to each other. If you were looking at the C, we got rid of the C right here. We pretty much have the same thing. Yeah, pretty close to it. Oh, sorry, that square root is not belonging in there. Yeah, yeah. So you see that if we get rid of this C, we actually have the same equation. Let's take a look at it in a different form. Okay, so this thing can be written out differently. We can take and divide. We probably should have done this. Maybe I should do this again, or live right now I should do it. Could write it up on this other page. All right, so let me write down here on the bottom. This is what we had on the previous page. PO over the square root of K minus M omega F squared plus C omega F, that squared. If I divide through by K, let's see, can I do that? If I divide through by, I have to divide, I'm not going to be able to do the math in my head. You just take a little trust that we would get this guy right here. We're going to ignore him. And that we end up left with this, and you'll note that this is going to be R right here. And note that's going to be squiggle, and that's going to be R. So we could reduce this if we wanted to. And we could also, by the way, let's pull this thing over to the side. XO over PO divided by X x, right? So this is the input. It's equal to 1 over the square root of 1 minus r squared plus, there's probably some things I could get rid of in here. 2 squiggle r squared. And that should be, and this right here will result in this graph, in which we have, once again, this frequency ratio. And notably, a lot of times they will, they also put in, if you're damping, right, these are all equal to squiggle, the different ones that you have. But when you have damping as 0, we have the same graph right here, all the way up, as we had in this much earlier graph. Let me get it back all the way up to there. So right there. See that graph right there? That is the same graph as, this is unfortunate, I kept all these in there. Is that. That's the same graph. We've just put them in. So let's do some problems and try to get this thing done. Get this thing out of here. I'm tired. I'll tell you what, oh, this is the next couple of examples kind of easy, so we'll see you soon.